Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. We've got a fascinating topic today: rethinking memory and AI, taxonomy, operations, topics, and future directions. I'm really excited to dive in.
Yeah, memory in AI is absolutely critical. I mean, without it, we're just building really fancy calculators, not intelligent agents. So this should be good.
I agree it's critical, but I think we're often using the term memory in AI way too loosely. It's not the same as how humans remember things, so rethinking it is definitely necessary.
Definitely. Current AI memory feels brute force, like we're throwing data at the problem and hoping something sticks. We need a more fundamental understanding.
Exactly. It's not just about storing information. It's about how that information is organized, accessed, and used. That's where the whole taxonomy piece comes in, right? Thinking about different kinds of memory, like short-term, long-term, procedural.
And the way those different types interact. I mean, look at current deep learning models. They remember patterns in data, but it's not like episodic memory where you can recall a specific event with all its context. That's a huge gap.
Right, and that's where I think the neuro-symbolic approach has something to offer. We need AI systems that can not only store information but also reason about it, make inferences, and connect it to other knowledge. Deep learning alone isn't cutting it.
I think it's even more fundamental than that. It's about how we represent information in the first place. Current systems are mostly coordinate agnostic, like a pile of vectors. How can an AI truly understand cause and effect or predict the future if it doesn't understand how things move and change in space and time?
That's a really interesting point, Donald. Thinking about spatiotemporal awareness, it reminds me of some recent work on memory consolidation, where the hippocampus replays sequences of events to the cortex during sleep. It's not just replaying the events, it's replaying them in a compressed and structured way that allows the cortex to extract general principles. Maybe that's how the brain manages different coordinate representations implicitly.
Okay, but isn't that what recurrent neural networks are trying to do? Capture temporal dependencies in data? I mean, sure, they're not perfect, but they're getting better all the time. With more data and more complex architectures, I think we'll eventually get there.
But are they really understanding the temporal dependencies, or just learning to predict the next item in a sequence based on statistical correlations? There's a difference between memorizing patterns and actually understanding the underlying relationships.
Exactly. It's like teaching a parrot to repeat phrases. It can mimic human speech, but it doesn't understand the meaning behind the words. We need AI systems that can understand the meaning of events, not just the order in which they occur.
So let's dig a little deeper into this taxonomy aspect. What are some of the key distinctions we should be making when we talk about memory and AI? I'm thinking about working memory versus long-term memory, declarative versus procedural memory. What else?
Well, in deep learning, we have things like LSTMs and transformers, which are essentially different ways of implementing long-term dependencies. Transformers, in particular, with their attention mechanisms, are really good at capturing relationships between distant elements in a sequence. That's getting us closer to true contextual awareness, wouldn't you say?
I still think it's fundamentally different. LSTMs and transformers are great at pattern recognition, but they don't have the capacity for symbolic reasoning. They can't, for example, infer that if A is a part of B and B is a part of C, then A is also a part of C. That requires a different kind of memory and processing.
And they struggle with hierarchical relationships. A transformer can learn, statistically, that a sentence often contains a subject and a verb, but it doesn't understand the grammatical structure in the way a human does. The knowledge is distributed, opaque, and difficult to manipulate.
That makes me think about how the brain stores information in a distributed way. It's not like we have a single neuron for every concept. Instead, concepts are represented by patterns of activity across many neurons. It's a much more robust and fault-tolerant system. Could we be leveraging that more in AI?
That's basically what deep learning is doing, right? Distributed representations across layers of neurons. The more layers and the more neurons, the more complex the representations we can learn.
But the problem is interpretability. We don't really know how those representations are encoded. It's a black box. With a symbolic approach, we can have explicit representations of knowledge that we can understand and manipulate.
Right, and that's crucial for explainability and trust. If we can't understand why an AI system is making a certain decision, how can we trust it to make important decisions?
Let's bring it back to memory operations for a second. Retrieval, storage, consolidation. These are all critical processes. How are we currently handling these in AI, and where are the biggest limitations?
Well, retrieval in deep learning is basically just pattern matching. You give the network an input, and it finds the most similar pattern in its memory, that is, its weights, and outputs the corresponding result. Storage is just updating the weights based on the input data. Consolidation? That's a bit trickier. Maybe that's analogous to fine-tuning a pre-trained model?
Again, it feels like a very superficial understanding of these processes. Retrieval in human memory is much more complex. It involves reconstructing a memory from fragments of information, filling in gaps, and contextualizing it based on our current state. Deep learning doesn't really do any of that.
And it's not just about reconstructing memories, it's about transforming them. We can take a memory and imagine it from a different perspective, or combine it with other memories to create new ideas. That kind of flexible manipulation is something that current AI systems really struggle with.
That reminds me of mental time travel, where we can imagine ourselves in the past or the future. It's not just about recalling a specific event. It's about using that event as a basis for simulating possible scenarios. That's a crucial part of planning and decision making.
Okay, but aren't we seeing some of that with large language models? They can generate text that's coherent and creative, even if it's not based on anything they've explicitly seen before. Isn't that a form of mental time travel, in a way?
I think it's more like they're remixing existing text. They're very good at combining different patterns and styles, but they don't really understand the underlying concepts or the implications of what they're saying. It's like a very sophisticated parrot.
Exactly. And they're very brittle. If you ask them a question that's slightly outside of their training data, they often produce nonsensical answers. They lack the common sense reasoning that humans take for granted.
So let's talk about specific topics within memory research. What are some of the most promising areas to focus on right now?
I think memory networks are really interesting. They allow you to explicitly store and retrieve information, rather than just relying on the weights of the network. And the attention mechanisms are getting really sophisticated, allowing you to focus on the most relevant information.
I'm more interested in knowledge graphs and ontologies. They provide a structured way to represent knowledge and relationships between concepts. And they can be used for reasoning and inference, which is something that deep learning struggles with.
I'm fascinated by the idea of building AI systems that can learn and reason about space and time. I think we need to develop new representation languages that can capture the geometry and topology of the world, and new algorithms that can manipulate these representations in a meaningful way.
All great points. What about the intersection of neuroscience and AI? I'm very interested in understanding the neural network structures of LLMs and those observed in the biological systems relate. Could a deeper understanding of the spatiotemporal dynamics involved in these models help us develop neuro-inspired AI architectures that are more efficient and robust than current deep learning approaches?
Well, understanding how the brain does it is obviously important. But I think we also need to be open to the possibility that there are different ways to achieve intelligence. The brain evolved under very specific constraints, and we don't necessarily need to replicate all of those constraints in AI.
I agree that we don't need to blindly copy the brain, but I think we can learn a lot from it. The brain is a highly optimized system, and it solved many of the same problems that we're trying to solve in AI. Ignoring that would be foolish.
I think we need to focus on the fundamental principles of intelligence, rather than just copying the details of the brain. What are the necessary and sufficient conditions for a system to be intelligent? That's the question we should be asking.
All right, let's start looking towards the future. What are some of the most promising directions for future research in memory and AI?
I think we need to keep pushing the boundaries of deep learning. More data, more computation, more complex architectures. I think we're on the cusp of some major breakthroughs, especially with unsupervised and self-supervised learning, allowing models to learn from raw data without explicit labels. That will drastically increase the amount of data we can train on.
I think we need to move beyond deep learning and explore alternative approaches. Neuro-symbolic AI, knowledge graphs, probabilistic reasoning, these are all promising areas that deserve more attention. And we need to focus on building AI systems that are explainable, trustworthy, and aligned with human values.
I think we need to develop a more fundamental understanding of how memory works across different scales and in diverse spatiotemporal contexts. We need to build AI systems that can learn and reason about the world in a way that's more like how humans do it. And that means understanding geometry, topology, and the laws of physics.
From my perspective, I'm very excited about the successful application of LLMs in biology, which presents a critical opportunity to explore the potential of integrating these systems with neuroscience models. The challenge lies in merging the symbolic reasoning capabilities of LLMs with the biologically grounded understanding of the brain. Can we design a framework for translating between the abstract symbolic representations and the concrete neural representations of the brain in a computationally efficient way?
That idea about LLMs in biology, it's fascinating. Analyzing the specific parallel processing techniques used in these language models could offer significant insights. I want to know which aspects of parallel reasoning are most crucial for enabling adaptive intelligence, and if the identified algorithms can be readily translated to other domains or models. If we can crack that, we could accelerate progress across the board.
I'm still skeptical. Focusing on language models feels detached from a deeper understanding of how the human mind works. How can we model the parallel processing and the adaptation mechanisms of the brain in a way that isn't purely statistical and data-driven? The current approach lacks a clear symbolic representation of the knowledge. We need that to make real progress towards AGI.
Yes, exactly. Different coordinate systems, for example, Cartesian, polar, geographical used in various tasks, seem to require completely different representations within the underlying algorithms. Developing a unifying framework for translation between these systems seems crucial for a more robust and adaptive parallel reasoning process. That's how we make AI less brute force in handling complex, real-world problem solving.
Those are all really exciting directions. And it sounds like we all agree that there's still a lot of work to be done. Thanks for the great discussion, everyone. It's clear that rethinking memory and AI is a critical step towards building truly intelligent machines.
Absolutely. And I'm optimistic that we'll get there eventually. The pace of progress is just so rapid these days.
I'm a bit more cautious, but I agree that it's a fascinating field, and I'm excited to see what the future holds.
Indeed. The journey towards AGI will be long and challenging, but the potential rewards are enormous. And the next steps will be the most important.
Thanks for tuning in to Cognitive Spirals. Join us next time as we delve into another fascinating topic in the world of cognitive science and AI.